Hello everyone, I'm Norman Wahlberger. Thanks for joining me on this new adventure in exploring research level mathematics. Today we're starting something really exciting. We're going to be looking at finite group theory, very classical, beautiful, and much studied subject, in a new way by connecting more strongly with linear algebra and some attendant geometry. So I'm proposing to think about finite groups as matrices. Okay, so this connects naturally with an aspect of finite group theory called representation theory. So in some sense, this is a natural and important part of traditional group theory. But my orientation is that by starting with the matrices as the central objects, we find all kinds of new ways of thinking about things, and we find new structures that are not so easily visible in the usual story. Now, my motivations for starting this course are twofold. One is the Dynamics on Graphs series, where I've been introducing the ADE graphs and mutation and numbers games. And if you've been watching that, which I hope you have, you'll know that there are these mutation matrices which play a central role. And associated to that, there are Cartan matrices. There's the Tits quadratic form, both on populations and weights. And there's all kinds of interesting connections with mathematical physics. So motivated by that and the development of that I've laid out, I'm seeing that some of those notions that are appearing there are actually easily generalizable. So I want to take some of those ideas and try to generalize them much more broadly so they apply to finite groups more generally. Okay, so that's one of my motivations. The other motivation is perhaps in a quite different direction, coming from my background as a harmonic analyst or a Lie group representation theorist. So I used to study Lie groups a lot. I'm still very interested in those things. And while Lie algebras are finite, in some sense, finitely specifiable because it's all about linear spaces, Lie groups themselves are much more complicated. You need to have some background in differentiable manifolds and vector fields and exponential maps and so on. And to be honest, the specification of Lie groups is a highly problematic subject. So going back to this distinction between descriptions and specifications, there's lots of ways of describing Lie groups. You know, it's the group of isometries of such and such structure or such. But to connect it directly with the actual official definition, to specify a Lie group, that's much more challenging. And so I think I'm not the only sort of person who has come to this realization that a really nice way of thinking about Lie groups is to think of them as matrices right from the get-go. Okay, that's a very powerful point of view, which is not the mainstream, but it's also has been explored. And so I'm going to be taking that orientation and applying it to the finite group situation. Okay, so you can read what I've said here. So I'm going to start today with this introductory talk. So I'm just going to lay out just a few definitions so we're all on the same page in terms of some basic terminology. And then I want to look at some main examples of these finite matrix groups. So these examples are going to be very familiar to you if you've taken a classical course in finite group theory, but you're going to see them in a novel way, and they're going to be pretty interesting for us. Okay, so the examples are, first and foremost, we want to have a wide range of examples so that we can have things to investigate. Okay, so in terms of basic terminology, by a number, I mean a rational number. So the field of rational numbers is our sort of default field, but down the road we also want to think about finite fields and maybe complex rational numbers, and maybe other fields as well. So the question is to how much of what I'm talking about extends to other fields is an interesting one, and I think that's also going to be interesting for you to explore. Okay, but let's stick at least now with the rational number case. So the main objects are going to be from linear algebra, a matrix. Okay, but I'm going to use the term an N matrix. Okay, so for a natural number n greater than or equal to 1, an N matrix is an n by n array of rational numbers. The space of n matrices forms an algebra, mat n, let's call it, over the rational numbers with identity matrix I sub n. That's the n by n identity matrix with ones down diagonal and zeros elsewhere. And I remind you that an n matrix A is invertible precisely when its determinant is non-zero. And sometimes we'll also talk about vectors, so we'll talk about row n vectors or column n vectors in the obvious sense. Okay, so that's just some brief linear algebra. We are going to have to touch base with matrix theory much more extensively as we carry on, okay? Because we want to frame everything ultimately in terms of this linear algebra setting. Okay, so what's a finite matrix group? Well, let's say you have a natural number n greater than or equal to 1, a finite n matrix group. Okay, so that's the terminology. A finite n matrix group G is a finite set of n matrices, which is closed under multiplication and taking inverses. So you take any two of these n matrices, you multiply them, you get another one which is still in the set, and you take the inverse of any one of them, you get another one which is still in the set. In particular, this set G contains the n by n identity matrix I sub n. The product of matrices, which we'll often denote by this X here, it's automatically associative because matrix multiplication is, so that we don't have to say that separately. In terms of some notation, we'll say that G is of dimension n, because the matrices themselves are n by n, and we'll write n equals dimension G. And if G has k elements, the number of elements, then we'll say it's of order k, and we'll write k as order of G or just absolute value of G. And if the dimension n is understood or maybe variable, we'll just refer to G as being a finite matrix group, and we'll introduce a shorthand for that, FMG, standing for finite matrix group. Okay, a few basic things. A commutative finite matrix group, well, that's just when G times H is H times G for any elements G and H. And in such finite n matrix group, we have left, in fact, also right cancellation. If G times H equals G times K, then H equals K. And the argument is familiar. If you have this relation, then you multiply on both sides by the inverse of G, which is existence by our definition. And then by associativity, you rearrange this to get H equals K. And symmetrically also, we have right cancellation. If we have H times G equals K times G, then H equals K. Another pretty simple consequence of things is that in a finite n matrix group, each element G is a matrix of finite order, meaning that there's some natural number, say R, such that if you raise G to the rth power, you're going to get the identity matrix. And, well, the reason is, so basically you take this element G, okay, and if the size of G is K, you might as well assume that K is bigger than 1. If K is equal to 1, we're just talking about the identity matrix, which obviously has order 1 already. So otherwise, you just take this element G and you look at the various powers of it, G, G squared, G cubed, up to G to the K plus 1, okay? And these are K plus 1 elements in this set, which has K elements. So by the pigeonhole principle, there must be some repetition. Two of these guys have to be the same. So that means we can write G to the L equals G to the M for some numbers L and M. We might as well assume that L is less than M. And then by multiplying by GL to the minus 1 on both sides of this, we get that G to the M minus L is equal to the identity matrix. So we've found a power of G, which is the identity matrix. So this makes it clear that the matrices that are involved in finite matrix groups are going to be rather special. They're matrices of finite order. So we'll have to learn a little bit about those things. Another kind of standard thing to do when you've defined an algebraic structure is you define some subgroups. So if H is a subset of a finite n matrix group, G, and if H is also closed under multiplication and taking inverses, then H is also a finite n matrix group. And we'll say that H is a subgroup of H. And also that G is a supergroup of H. This latter terminology is not at all as common as subgroup, but it makes things a little bit more symmetrical. So H is a subgroup of G, equivalent to G is a supergroup of H. And we'll write less than or equal to for this relation. So H less than or equal to G means that H is a subgroup of G, and or equivalently, G is a supergroup of H. And this allows for the possibility of equality. And this is clearly transitive. If H is a subgroup of G and G is a subgroup of L, then H is a subgroup of L. Now, in terms of determinants, since the basic rule for a determinant of a matrix is that the determinant of a product is the product of the determinants, it means that if you take the determinant of a power of some matrix, say x to the n, that's the same as the determinant of x to the n. And if we're talking about some matrix X which has finite order, so that some power of it is the identity matrix, which has determinant 1, it means that the determinants of such things have to be strongly constrained, right? Because the determinant has to have the property that if you raise it to some power, you're going to get 1. Now, in the rational numbers, there's only 2 such numbers that have that property, namely 1 or minus 1. So any element of a finite matrix group must have determinant either 1 or a minus 1. And then if we look at the set of matrices with determinant equal to 1, so let's say we have a FMG called G, and we consider the set of matrices with determinant equal to 1, that's forming a subgroup. Let's say G sub 0 of G. A subgroup because if you multiply 2 of them, determinant 1, the product will also be of determinant 1. Okay, so we'll call this the unary subgroup of G. And okay, this is in fact normal. We don't actually know what normal is. Maybe I'll just remove that for now. We don't know what normal means yet. If K is any element of G which is not in this unary subgroup, then the map G to G times K, okay, is a bijection between G0 and its complement. Because if G has determinant 1 and K has determinant minus 1, then G times K will also have determinant minus 1. And you can go backwards by multiplying by K inverse, which will also have determinant minus 1. So that's showing that the unary subgroup of FMG group G is going to be exactly half the size of the big group. Okay, so the size of G, or the order of G, is 2 times the order of G0. Now that's if there's an element in G which is not in G0. If, however, G equals G0, so in other words, if all the elements of our FMG are having determinant 1, we'll say that G is a unary FMG. And if G and H are finite n matrix groups, then their intersection is also a finite n matrix group. Okay, so that's sort of obvious. If you have one set of matrices and another set of matrices, but they're all in the world of n matrices, then the intersection is going to have the property it's going to be closed under multiplication and taking inverses, because each of the 2 individual sets is closed under those 2 things. And so this G intersect H is going to be a subgroup of both G and H. A much more subtle issue here concerns what happens when you have these 2 finite n matrix groups G and H. Can we find some larger finite n matrix group K which contains both of them? Are they subgroups of a common finite n matrix group K? Okay, so I don't know the answer to that question or how to approach it in general. So conditions on H and G that guarantee the existence of such sort of a common supergroup seems like a major challenge. This is the kind of question that doesn't really make sense in ordinary finite group theory, okay? Because in finite groups, if you have 2 finite groups, they're not connected in any obvious way. But here we're assuming we have 2 finite n matrix groups, so they're all sitting in the world of n by n matrices. So we can ask this question. And if there is such a k, okay, then there will be a minimal such k, and it's interesting to ask, whether this kind of thing happens. So some related questions in this direction. So given a finite n matrix group G, can we always find a proper supergroup K? In other words, an FMG, also an n matrix group, K, such that G is a subgroup of K, but G is not equal to K. So can you always extend? Are there finite matrix groups G which have no proper supergroups that can't be extended, sort of maximal ones? And are there FMGs G which have a non-zero but finite number of proper supergroups? If so, can we characterize such? And in case G does have this sort of finite supergroup property, then the collection of supergroups will be closed under intersections, and so forms a potentially interesting poset ordered by inclusion. And it's natural to extend this also to the poset of subgroups of G, so giving us a poset contains strong information. Can we come up with some interesting examples of such? So these questions already suggest to us that this theory is going to be a little bit different from usual finite group theory. And I suspect it's going to be really fertile ground for investigation by amateur mathematicians. So at the heart of any mathematical theory, there are examples. And it's really important to have a wide range of examples so that we can really freely explore the various aspects of whatever theory we have in question, right? So let me give you some advice. If you don't have a lot of examples in some proposed theory, steer clear from it, okay? It's not perhaps a worthwhile place for your investigations. Look for mathematics where there's rich examples. So with finite matrix groups, there's lots of rich examples. Let's have a look at some of them, starting with a very simple one. So the simplest finite matrix groups have just one element, the identity matrix. Okay, so we could define for a natural number n greater than or equal to 1, the identity n group. Okay, T sub n, let's say, for lack of anything else, T sub n, which just consists of the single identity matrix I sub n. Okay, there's only one product here, I sub n times I sub n equals I sub n, and only one inverse. Okay, so it's clearly a group. A little bit more complicated, just a little bit more complicated, is what we might call the parity n group, where you consider the identity matrix I sub n and its negative. And I often like to denote negative with a bar over things. So I sub n bar, that's the same as minus I sub n. And here is the multiplication table of this FMG, which is a useful construct, okay, where we just record the various possible products, with the convention that if we're in a row indexed by a group element A and the column indexed by a group element B, then what should be here is the product of this one times this one. So this element here is the product of this I sub n times this I sub n bar. Okay, and here's the obvious multiplication table for it. And clearly, just in the top left corner of this, you see the multiplication table for the earlier identity n group T sub n. So T sub n is a subgroup of P sub n, and in fact T sub n equals P sub n 0. Is that really correct? No, that's not actually correct, is it? Because it's correct some of the time. If n is even, okay, if n is even, then this negative I sub n will still have determinant equal to 1. So it will not be the case. So let me just modify that and say clearly T sub n is a subgroup of P sub n. So the next example is the Klein fore matrix group. Okay, with these four 4x4 matrices. The identity, this one here we might call it A, this one we might call it B, this one we might call C. These are all permutation matrices in the sense that there's a single 1 in each row and column. If we act on the right, say on 4 vectors, on row 4 vectors, then this one keeps everything where it is. This one here interchanges the first and second elements along with the third and fourth elements. while this one interchanges the first and third elements along with the second and fourth elements, while this one interchanges the first and fourth elements and the second and third elements. And it's easy to see that the multiplication table is like this. Okay, we see this is a little commutative group with 4 elements. For our next example, let's introduce, first of all, the notion of a cyclic n matrix. So n is a natural number greater than or equal to 1, and let's say that k is some number between 0 and n minus 1. So the cyclic n matrix C sub nk, it's an n by n matrix, okay, whose ijth entry is either going to be 1 or 0. And it's going to be 1 precisely when I minus j is congruent to k mod n. So when, say, when n is 3, so here's the case when n equals 3. When k is 0, this condition is I minus j is congruent to 0. That means that I equals j mod n. That's giving us 1s along this diagonal. When k is equal to 1, say that I is equal to j plus 1. So the I is, here this is like the 2, 1 entry, right? The I is 2, the j is 1. This is the 3, 2 entry. The 3 is 1 more than 2. And this is the 1, 3 entry. The 1 is 1 more than 3, which is the same as 0 mod 3. And here is C3, comma 2. So these matrices are constant on diagonals. Diagonals sort of parallel to the main diagonal, okay, and have a sort of a diagonal of 1s in some place, and then also something else on another one. So here's also some examples with C4. So now we can define the cyclic n matrix group, okay? We can define the cyclic group in this context, in this matrix context. So for a natural number n greater than or equal to 1, the cyclic n matrix group C sub n, that's the name of the group, okay, it's going to consist of the set of such matrices that we just talked about, these cyclic n matrices, C sub nk, where k runs from 0 up to n minus 1. Okay, so when n equals 1, there's only one such matrix, the identity matrix, the 1 by 1 identity matrix. When n is 2, we have, this is C sub 2 comma 0. This is C sub 2 comma 1. C sub 3, well, we're just getting these 3 matrices that we've already seen. And C sub 4, we get these 4 matrices. So we start with this diagonal of 1s, and then we sort of move that diagonal down 1. Okay, so now the diagonal is there. But also, one of them goes up to the top there. Okay, and then we move it down again, so we get this one here, and we get another corresponding diagonal there, and then here and here. Okay, so these are the cyclic n matrix groups. And it's an easy exercise to see that the product of any two of these is another one. In fact, Cn comma k times Cn comma L equals Cn comma M, where M is just the sum k plus L mod n. So in fact, yes, this is a commutative group. And in fact, it's a cyclic group, meaning that each element is a power of some single element, that single element being called a generator of the cyclic FMG. In this case, an example of such a generating element, it's not unique, but an example is Cn comma 1. Like this one here is a generator of this group, because if you take this thing here and you raise it to the second power, you're going to get this thing. You raise it to the third power, you get this thing. You raise it to the fourth power, you're going to get the identity. And in fact, any cyclic FMG, whenever you have a group, an n matrix group in this context, of which has a cyclic property that there's a particular element so that all the others are powers of that particular element, then that's necessarily commutative, because powers of a single matrix always commute. If you have some matrix X and you look at its various powers, x squared, x cubed, etc., they always commute. So this is a commutative group in general. Now, you might think, if you're sort of a classical group theory student, you've learned about the cyclic groups. If we view them as multiplicative groups, what would be your sort of incarnation of a cyclic group? Chances are you're going to say, we can realize these things as the nth roots of unity in the complex plane, where we take the unit circle in the complex numbers and we look at the nth roots of unity. So we're subdividing the circle, creating a regular polygon with n sides. But from other lectures of mine, you'll know that creating that regular polygon is a highly problematic thing. Okay, you can say and consider the regular 11-gon, but how do you construct that regular 11-gon? So actually what you really need is, in order to specify the x and y coordinates of the vertices, you need things like, cosine of 2 pi over 11 or something. You need to create an infinite process in order to get the x and y coordinates of these vertices. So that description of what a cyclic group is in fact very problematic. It's implicitly invoking some infinite processes from analysis. That's what you're really doing. So this approach here, where we embed the cyclic groups as matrices, maybe they're a little bit big, but it's completely algebraic. And of course it connects with the usual sort of interpretation of a cyclic group as sort of cyclically rotating. So for example, in the n equals 3 case, we take one of these matrices here, like this one here, and act on a row vector. Well, it's going to rotate the vector, okay? But if you act on a column vector, it's also going to rotate the elements, but in sort of an opposite way. So whether it's a kind of a clockwise or anti-clockwise rotation, it depends on whether you're acting on the row vectors on the left or column vectors on the right. And similarly, here's the other one. It does sort of the opposite. So cumulatively, this cyclic group C sub 3 acts on row vectors as group of rotations, and it acts on column vectors also as a group of rotations, sort of cyclical rotations, but it does so in kind of different ways, okay? So, cumulatively, the effects are the same. And this is an interesting point that we'll be seeing over and over again here in this subject, that when you have a matrix group, there are really these two actions. Okay? There's the action on the row vectors and there's the action on the column vectors. And neither of these is intrinsically preferable. It's exactly the same story that we saw in the dynamics on graph series, right? Where we have mutations on one side and dual mutations or firings on the other side. And it's the interaction between these two actions, if you like, that generates so much of the interest of the story. Okay, so you can see that we're looking at things a little bit differently from a classical finite group theory course. Okay, excellent. So we have the cyclic groups. Well, what about the dihedral groups? Okay, the dihedral n matrix groups, D sub n, these are supergroups of the Cn matrix groups. Okay, and they're obtained by adding another n matrix. Which one? Well, a rather special one also, which we might call the cross-diagonal identity n matrix, L sub n. Okay? And that's a matrix like this that just has sort of ones on this sort of cross-diagonal, not going this way, but going this way. Okay? So what we're doing is we're adding this thing to the cyclic groups that we already defined. And then also, of course, necessarily adding products obtained by taking products of this thing here with the cyclic group elements. And it turns out that gives a bigger group, which is exactly twice the size of the original cyclic group. So for example, if we have D3, so there's the original cyclic group C sub 3, we've added this one here, and that's the product of this with this. If you take the product of this with this, you get this one. When you take the product of this with this, you get this one. And here is D4, where you have the original C4 there, then you're adding this cross-diagonal guy, L sub 4, and then here are various possible products of this times this, this times this, this times this, giving you 3 more matrices. Now, a question would be, well, how do we know this is closed? So multiplicative closure of these dihedral groups follows from this relation that when you multiply one of the CNK matrices by the L sub n on the right, you also get a product of L sub n on the left times another C matrix, but Cn comma n minus k, so the reflected or the symmetrical one on the other side. So it's the presence of this relation together with the fact that Ln squared itself has order 2 that allows you to check that these dihedral groups actually are closed under multiplication and inverses, so that we really have honest FMGs. That's a really good exercise for you, so please check this claim. Okay, there's a special case that's pretty interesting. This D sub 4 case is particularly interesting. It's as it is a supergroup of the Klein matrix foregroup and connects in an important way with the algebra of 2 by 2 matrices. And I have some lectures on dihedrons. So here's another manifestation of it, in the sense that the multiplication table of the following agrees up to relabeling with that of the D4 group that I just defined. So later on we'll talk about isomorphisms and homomorphisms, and we'll be able to say something, in that language. But at this stage here, you should just think about this. Here's another FMG, okay, which is different from this one. These are 4 by 4 matrices. This one here is a bunch of 2 by 2 matrices, but nevertheless they have essentially the same algebraic structure, and that if you wrote down multiplication tables for them, you'd see that they're corresponding. The multiplications are really the same up to relabeling. Okay, so what do we have here? Well, we have matrices E, I, J, K. These will be somewhat familiar if you've watched my dihedron lectures. And over here, the next 4 are just the negations of these ones here, so with some bars in them. So we might call them E bar, I bar, J bar, K bar. And so these, this one here, maybe we call it D sub 4 2 or something. It's actually isomorphic to the previous D sub 4, but not equal. And here's, when you look at it this way, you can sort of see the role of the dihedral group, because when you act, say, on row vectors x and y, then you can see that the action of these guys is like a traditional dihedral group acting in the plane as rotation symmetries, rotation and reflection symmetries of a square in the plane. And as a little exercise, you might actually try to figure out where is the Klein matrix foregroup sitting inside here as a subgroup of this thing. Okay, now we come to what's pretty well clearly the most important general family of examples of FMGs, playing a huge role in the entire subject. And that's the symmetric groups. But in our case, the symmetric N matrix groups, okay, and Sn. So what does that consist of? Well, that consists of the permutation matrices, which are of size n by n. And a permutation matrix is an n by n matrix having exactly a single 1 in each row and column. Otherwise, the entries are 0. There are obviously n factorial such matrices. And for the low dimensional cases, we can write them down easily enough. So there's 2 of them in S2, there's 1 in S1, and here are the 6 permutation matrices in the 3 by 3 case. Now, let me just reiterate, okay, that I've already talked about this at some length in the dynamics on graph course, but we should think about these matrices as not exactly groups of permutations of a particular set, okay? So a matrix like this can act on row vectors, acts on the right on row vectors. It acts on the left on column vectors. Okay, so yes, we can interpret these things as permutations of a set, maybe the set of row vectors, or permutations of the set of column vectors. But in fact, you could also act with these matrices on other objects, like other size matrices. So it's really not the action as permutations of a set that's primary for us here with this point of view. What's primary is just thinking about these things as matrices. And that's something that I've already emphasized in the Dynamics on Graphs course. And closely related to these are the alternating n matrices. The alternating n matrix group A sub n, okay, which is the unary subgroup of Sn. That is, we look at the subset of these things which have determinant equal to 1. Okay, so for the low dimensional cases, what we have, the A1 is just 1, the A2 is just a single element, the A3 just consists of these first 3 guys. These are the determinant 1 things. They correspond to the rotations in the usual story. The other ones sort of correspond to reflections. And in A4, instead of having 24 elements, we have 12 elements. And here they are. So these are the matrices in the alternating group A sub 4. And finally, our last example is coming from the Dynamics on Graphs course, which is really a motivation for this whole story, where you may remember when we were talking about the ADE graph A2, just 2 vertices joined with a single edge, the mutation matrices S1 and S2 generate the Weyl group, which in this case is this group G with 6 elements containing also these other 2x2 matrices. So this is the group, the Weyl group in this case, formed from the mutation game on the graph A2. And of course, as a group, this turns out to be the same as S3, okay? But in general, what we can do is for any ADE graph, okay, we can create a Weyl group in a similar way, because we know that for the ADE graphs, the mutation matrices generate a finite group. Okay, we have these mutation matrices, 1 for each vertex of the graph. Okay, and then the group they generate is the Weyl group, and that's a finite group if we start with a graph X, which is an ADE graph. So there's lots of interesting ADE graphs, and so that generates all kinds of interesting FMGs for us, the classical Weyl groups coming from the ADE graphs. So it's actually this example here that we're particularly interested in sort of generalizing. We want to see to what extent do the remarkable things that are happening in this story over here that I'm describing in the Dynamics on Graphs course, to what extent are there analogs of that for these more general FMGs? So these examples that we have here today is a good starting base, a good grounding for investigating these finite matrix groups.